taxa puja o baixa no és acumulat.
No es transmet en directe.
No es transmet, cada vegada no es transmet en directe. Per tant, està a la pàgina web, igual com està això després. Per tant, en principi, si hi ha això a la pàgina web, igual que la generació secundària, no veig cap diferència concreta.
No, sistema interdisciplinar.
A tu te van gravar, no?
Sí, sí, sabes. ¿Has tú?
No té cap.
¿Tú estás consciente que te grabes?
Sí, sí.
Okay, so let's start. This is the master thesis presentation of Miquel Alfaras. 25 minutes, 30 minutes. Okay. We are flexible, but not too much.
I'll try. Okay. Welcome everyone. I'm presenting my master thesis on Photonic Reservoir Computing, and in particular a study of a Mach-Zehnder modulator. And this is a thesis that has been supervised by Ingo Fischer and Miquel Soriano. First of all, I'd like you to pay attention to this image. We have some information that, depending on the dimension that is projected, looks different. But by combining all the projections, we can retrieve characteristics of the whole information. Say you don't see the cylindrical form, neither here. But with the combination, you can extract this. I want you to keep this in mind. As an outline, I'm going to be talking about some computational tasks. I'll present the reservoir computing, in particular photonic reservoir computing, based on a Mach-Zehnder modulator as an injection component. And finally, I'll show you some characterization results and draw some conclusions. Well, computational tasks. When we think about computers, we use computers every day. Like when you need to do numerical calculation, say integration, differential equations, you use a computer to solve them. And this is the power of these machines is tremendous. However, when we pay attention to other tasks, our central processing unit, the brain, is much better. Like, say, pattern recognition. You can see a tiger here. Evolution has trained you to do that. Or, say, signal processing. You can extract features of a signal. You can say, this is sinusoidal, this is triangular. And all of this in a snap. Like, in question of hundreds of milliseconds. Say, say someone calls me now, and you say, oh, that was Mozart. That was the Turkish man. And only in a question of hundreds of nanoseconds, you realize that this is Mozart. I say, if we are talking into a crowd environment, you can trace my conversation and follow it. Or here, if I tell you, find the umbrella, you find it. So we're going to be discussing an alternative computational approach that is a bit better when addressing this kind of tasks. And this is the case of reservoir computing. It comes from the field of artificial recurrent neural networks, and it's based, well, it's brain inspired, it's based on nonlinear transients, and on a high dimensional mapping, you map information into a space of many different neurons. And I'm going to show you also that it has a layered structure. Say we have this input signal. So we take the signal and we map it to a whole number of neurons. And for each neuron, we get a different response. All of them are true. And it's by the combination of all of them that we get the analysis capability. And this is perfect to analyze sequential information. About the properties, well, the system has to exhibit a fading memory. Why is memory important? Because when the system provides responses to these, if I want the computer to tell me that we have two peaks here, when it is analyzing these, it has to be able to retrieve information from the previous input. So it is based on this kind of loops that we see here. That's the reason we say, well, one of the reasons we say it's brain inspired. And these recurrences it's what provides us with memory. Consistency. If you give different inputs to your computer, say to identify cubes, the response has to coincide because all of them are cubes, different cubes. But for the task that we are interested, the response has to be the same. However, if we input different but similar, well, not so similar inputs, we need the computer to provide us with separability. We need the computer to tell us, no, this is not a cube, but this is a cube. So these three properties are key: memory, separability, and consistency. How does it work then? Well, we have an input layer. This is the layer structure that I was mentioning. And we map whatever information that we have here onto a high-dimensional space of neurons. And then these responses that we get from a nonlinearity, these responses are taken, just linear combination, with these weights, and we get a result. So we say, okay, my computer is identifying that I'm presenting cubes to the system, for example. So in the end, we have just a matrix multiplication. Once we have the weights, we have that weight times the responses that we collect here in the reservoir of neurons. This is what provides us the output. How can we achieve this? Well, we need the weights. We need to go through a training procedure. Say we train our system to identify handwritten files. I give it an input, and this, by the nonlinearity, is mapped to a high-dimensional space. I give it another 5, different 5. This is mapped. So on and so on. And then we collect the responses, and we know that we want this target. So we train the system in a way like that. We want that the weights times the reservoir responses give me an output which is 5. So we perform a matrix inversion there because we don't know the weights yet, and we, through a linear regression, we get this vector W, which will be used then as simple as a matrix multiplication to take our neuron responses and bring it to the result that we want. So for example, if the system is properly trained, this input, when we apply the 5 identification, we get this output, which tells us that this is not a 5, but this is a 5. And well, so far we've seen some nonlinearities used to build these reservoir computing approaches, and one could be nonlinearities present in fluids. Another could be the case of atomic switches that enhance high harmonics, which are nonlinear. But I'm going to be focusing on nonlinear photonics. Why do we want to work with light? Well, the benefits: speed, low power consumption, and low interference. For example, take this image of a fiber cable. We have 72 optical fibers and no interference. And what I'm showing now is something that was developed here at IFISC, which is a step further, that from one single nonlinearity, you can get a whole reservoir of neurons, but from one single element. And this was a delayed coupled laser, coupling light to itself. How is this achieved? We take whatever input that we have, and we divide this information into tiny pieces. This is time. Information that needs to be introduced in an injection time tau, let's say. We divide it, and so we virtually create a reservoir of n neurons that provides us with different responses. How do I know the difference between the responses? Well, because it happens at different times. So this is what's called time multiplexing, that makes able that you go from one single nonlinearity to a multiple response reservoir. So we say we apply an n mask of duration tau. Let's say this has a duration, this has the same duration, and we've divided this information into tiny pieces so that we get this reservoir. It's a particular case of what we exposed before, but still the achievements are amazing, and there are, well, this is how information is inputted. We take an electrical signal, and with the laser and the modulator, this is codified into light. We modulate an input, which is electrical, and we get information which is modulated in light intensity, and this is done by the Mach-Zehnder modulator. Well, this is just what I explained, and this is a result that was what was obtained here. This is the case of the laser, delayed feedback laser, and for example, this mask information is input, and you can see that how we input one piece of information, then we input the next. But for example, look at the response. Look at the input for information number 4. Whatever information that we are inputting is affected by the previous information. So this is so low because it comes from this relaxation. At every input step, we have some relaxation. This, in the case of the laser, is the relaxation oscillation. So what I'm highlighting here is that we get loops, or we get memory connections, because it's the way we designed the experiment, so that every piece of information is affected by the previous one. And so far, by doing this, some achievements have been obtained here in the institute. For example, researchers were able to perform a spoken digit recognition, and not only identify a number that was spoken by different female speakers, but also telling you which of the speakers was telling this number. Another case, matrix and vector operations. This was realized with this reservoir. And another case, chaotic time series prediction. And well, I take this system, we took this system based on a single nonlinearity, and we studied this task, which is give the computer a set of randomly generated numbers, and extract from one number, extract the previous information. This is a memory-dependent task. If you don't have memory, you cannot do that. And we train another task, which is do the same, but with 2 steps. From 0 to 12, you have to get me 0, 4, 6, 8. And we did that, and we got amazing results. That the system with the delayed feedback laser has memory. What's even more interesting is when we take out the feedback, when we remove the memory component, so we get this setup only based in the Mach-Zehnder modulator, and we try to do the same. And surprisingly enough, we see that for a mask length of 400 nodes, we get, this is an indication of memory, and for a mask length of 400 nodes, we get memory. But how can this be? I mean, there is no delayed feedback laser. So where is the memory coming from? So this is the key of my study. We focused on the Mach-Zehnder modulator, the only possibly affecting element in this setup, because we have polarization control. Okay, we have optical attenuation, but this is just control. Memory could be coming from the Mach-Zehnder modulator because we now have no delay at all. So I present you a selection of experimental results. This is me in the lab. This is the element that I'm studying, this red electro-optical element. This is the Mach-Zehnder modulator. And well, first of all, we gave the system a couple of pulses. This is electrical pulses. And we see that, for example, looking closer at here, when we modulate this is electrical signal modulated optically modulated by the Mach-Zehnder. And we see here a tiny oscillation, and we say, how can this be? Where is this coming from? And we had a look at the Fourier transform, and that's it. There is a low frequency component here. Could it be that this low frequency component is introducing memory to our system? Well, this is what we want to find out. If we compare the modulated signal with electrical signal, we see that in the electrical case, there is no oscillation at all. There is a bit of crosstalk, and this could be providing a low range memory, but it's something that has to be analyzed. So we were thinking, okay, how can we characterize this system? We might think about a task that can use this memory. So we focused on fiber optic communication and say, imagine you live in the West Coast in US, and you want to send a message to, I don't know, Baltimore or Chicago or New York. When this information is sent to the internet, it gets to a hub in Los Angeles, and it has to be diverted to get to the point, to get to the destination, say Chicago, Baltimore, or whatever. So there is a routing process, and this is codified in the information. So we focus in the header that is included in the information, and we devise a binary header recognition task. What's in a binary header? Well, we have 320 bits. And inside, we have things like the protocol that it's being used, the source address, and the destination address, so that the hub in Los Angeles can divert information to the destination that you want to achieve. So we designed this, which is bit recognition. And for example, here, taking windows of 2, we get the conversion from binary to decimal. We have 1, 0, which is a 1. We have 0, 1, which is a 2. 1, 1, which is a 3, and so on. And we can do the same for the 3-bit case. We have a 5 here, we have a 6, and so on. These are different tasks, but it's something that we want to try with our system without delay to say, okay, the Mach-Zehnder has memory, or the Mach-Zehnder is not providing memory. And we did that. It's the same experimental setup that I showed before. And we perform a training. We take these binary digit combinations, and we, for the different responses, we perform a linear regression. And we were using a mask now of 6 values. This usually we work with 400 node masks for the time multiplexing, and in light we find 6 values of modulation, and we can either have a bit equal to 1 or a bit equal to 0, but for sure we don't work with zeros because that would be confused with noise. We take some value, I think it's 0.5, and this is 1.0. And what I'm going to show now is how the system performs with the recognition task. And as a reference, I give you this image that shows here the error percentage, the number of bits that we are considering, and here we observe the trend. And as reference, we're going to focus on the random values. If I tell you to draw me a number 0 or 1, that's 1 bit, you have 50% probability to guess it or not. If I tell you to draw me a number among 4, because with 2 bits we have 0, 1, 2, and 3, you have 25% probability of success, and so on. So we're going to analyze the results in the context of these bit error plots. And how do we evaluate? How do we get an error value? Well, for example, for this 11-member target, say if we get this output, we know that comparing, there is 1, 2, and 3 outputs which are wrong. So this would correspond to a 27% error, more or less around here. Still better than random. So this is my first result, the first result that I got at the beginning of the summer. And we see for 1-bit recognition, we have no error at all. For 2-bit recognition, in this red curve, we have around 4% error. But this decreases. It is still below the random value, because if you think about 3 bits, you have 27% error probability here. So it's much better. What is this telling us? Well, this is telling us that the system has memory, and only provided by the Mach-Zehnder. If we do another task, which is this green curve, is based on 4 different classifiers. If we consider the 2-bit case, we have a classifier for the zeros, another for the 1s, the 2s, and the 3s. By combining all of them, we get an output. It's slightly worse performance. As you see, the green curve is always above the red curve. And it has a compromise in speed, because before we were working with 1 single task, now we're combining 4. And as soon as you move to 6-bit recognition, you have 64 classifications. So from now on, I'm just going to show you the red curves, which show a rather better performance. And we say, okay, if this is able to recognize information, that means we have memory. And we looked at one input of information, and you can here see the electrical input, which is the blue curve, and the modulated light. And if we do a zoom here, zoom in, we get this optical oscillation. This is what's responsible for the memory. And this has a periodicity about 100 nanoseconds. So there are low frequency oscillations, and these introduce memory into my system. So I performed several characterization experiments, and maybe we can focus on the modulation point, we can focus on noise reducing procedures. And for example here, for the modulation, the Mach-Zehnder modulator modulates with a sine curve. That means that you input an electrical signal and you get this optical output. But since we don't want the computer to be confused, we have to restrict this to a region which is bijective. Because, say, input number 5 volts and input number 21 volts have the same output. This would be confusing to my computer. We wouldn't be respecting the separability condition. So in order to do this, we place an electrical attenuator that takes the input from the sinusoidal rise curve, which is this. This is the experimental result. This is what we achieve through calibration. And for example, if we, instead of taking this window centered at 977 volt, we would take a wider window, this would be confusing for the computer. And we can see this here. This is what we had before, good performance for low number of bit recognition, but now, with a wider window, you cannot, because the computer is confused. How can we improve the results? Well, one way would be to consider the oversampling. We are injecting information with the arbitrary wave generator at a constant rate, say 5 gigasamples, which is the case that I was showing before. And the oscilloscope, on the other hand, is reading data at 40 gigasample per second. So there is a factor which corresponds to average. I don't know if this is clearly seen here. We have several points that constitute my information. If you have a different ratio, say you move to 1 gigasample injection instead of 5, you get a much higher oversampling factor, So in the end, you are averaging noise in this procedure. By averaging noise, which is moving to a slower injection, you get this curve that we were observing before, the pink one. Now it's the red one for the 1 gigasample per second. So with this we achieve some kind of noise reduction. Another way to improve the results would be just to go to the acquirement, the measurement, and take averages of the oscilloscope sweeps. Say, instead of one sweep that I was presenting before, say we take 10 sweeps or 100 sweeps, and you can see how error diminishes a lot. But of course, all of this has a compromise, and it's time. By taking more sweeps, you take more time to compute a result. And just as a reference, we work with signal-to-noise ratios of about 25 decibels, which, well, for example, in this case, this is an example of my obtained traces in the oscilloscope, and it has to compare to the noise. If this is too low, this would be confused. So we'd like to reduce the signal, to increase the signal-to-noise ratio, reducing the noise. And this can be done by oversampling or by averaging in the scope, for example. And on top of this, there's a limitation that we are using a photodetector. And okay, you can say, yeah, why don't you move to higher scales, put more light into it? But there's a limitation. You cannot exceed the 3.2 milliwatt, because then you'll burn the photodetector. Another experiment that I was focusing in was the external memory injection. That is, we can move from the red curve to the green curve or the purple curve. What is that? Instead of injecting 1 bit every cycle, we can decide to inject 2 bit or 3 bit or 4 bit, and then you get the same behavior but shifted. Now it's cool. You get 3 bit recognition without error, but it's like an artifact. We are creating this memory just in the injection step. And another result that I like a lot is this exclusive individual task, which is from the present responses. This is really very much related to the TOE task that I was showing at the beginning. From the present responses, get the previous information. And not only one time step, but you can do these multiple tasks with multiple time steps. So, for example, here, going back 1 step, we get this recognition, 30% error. Still better than random. But what's surprising is that this plateau-like, this almost straight slope, is below the random for almost 20 steps. So that is the clearest image of memory that we have. And the same happens for the 2-bit, which you are below 75%, for example. So this is telling us that we have memory. And looking at the cycle length, for example, we saw some periodicity changing the number of nodes that we input. You see that this performance decreases and then increases again. So there is something with the periodicity. We looked at it into an aggregate plot, say taking all the recognition performances all together, and you see this oscillation, which is with a periodicity of 80 nanoseconds. You move from a low memory case to a high memory case. So this is in consistency with the previous results. We have memory here, and we have a low periodicity, a low periodicity, which is enhancing memory. And we can see that for every single bit. Well, for 1 and 2 bit recognition, you get good performances, then you cannot analyze. But for the rest, it's something which is consistent and it is exhibited in any case. So as conclusions, we can say that we observe memory just provided by the Mach-Zehnder modulator, and this is a general behavior. It is consistent, and through our study, this is reproducible. We've seen that through several realizations on the experimental side. Moreover, could we model this? I mean, we've realized that there is some interesting behavior here. There is some coupling introduced by the modulation. Can we get a dynamical equation so that we could observe bifurcations or, let's say, changes of behavior from the analytical point of view? Could we apply this approach to other tasks? Can we think of other tasks that can benefit from this? And well, it's an open door, and it's an experimental point of view that needs to be explored. So as references, I cite here several of the studies that have been conducted here at the Institute. And nothing else. I'd like to thank you all for your attention.
Thank you very much. Miquel.